All right, let's do some probability. There are 7 days in a week. I think I'll do all of these. Sound good? Cool. 7 days in a week. What's the probability that you select a day at random in 4 weeks and it's a Friday? Okay, so we're going to select one day. We've got a 4-week span. We just randomly say, boom, this day, and we get a Friday. So we would be looking in a window from May the 1st to the 28th. So all of those days. If you look at all those days, how many are there? There's 28 of them. How many of them are Fridays? 1, 2, 3, 4. So we got a 4 out of 28, which is 1 out of 7. Just like 1 week, you got the same probability in every week. So it's still going to be 1 out of every 7 days. That is the number of favorable outcomes over the number of possible. Now let's move on to an extension of the counting principle. If we wanted to know, so remember, probability, just like I said, is favorable divided by possible outcomes. So how many different possible outcomes are there for flipping a coin twice? So we're going to flip a coin twice. We're going to roll a die, and then we're going to draw a card. How many ways could that go? If we want to know how many ways that could go, the counting principle says we just look at the number of possible ways for the first event. So we flip a coin, 2 ways that could go. We're going to flip a coin again. There's 2 ways. And then we're going to roll 1 die. That's going to have 6 different ways that could go. And then we're going to draw a card out of a deck. There's 52 ways that that could go. And if we multiply those all together, we come up with times 2 times 6. Come up with 1,248. Whoa. Come up with 1,248 ways that that could happen. Well, what's the number of favorable ways that that could happen? Well, one side of a coin is heads. We want to do that twice. How many possible ways are there to roll less than a 5? 1, 2, 3, and 4. So there's 4 ways that could happen. And then draw a jack out of a deck. If you don't know, there's 4 suits in a deck and they all have jacks in them. So there's 4 of those. Multiply straight across and you get there's 16. If you did that, there's 1,248 possible ways that that could go. 16 of them would involve all 4 of these things happening at the same time. So we can do 16. Whoops. You hit math, enter. It says, hey, that's a 1 out of 78 chance of that happening for you. Well, what about flipping 4 heads in a row on a fair coin? So again, you think of it as possible, favorable over possible. Or we can just do, here's the probability of the first event. We have the same probability of it happening again. Notice these are all independent of one another. We aren't more likely to flip heads if we've already flipped heads. We're equally likely to flip heads. That's one of the fallacies of probability. You look at it and you're like, oh, we flipped 3 heads in a row. We're bound to get a tails this time. Well, not really. They're all independent of each other. It's the same coin. You've just already flipped it 3 times. So this is 1 out of 16. Thanks for coming to my TED Talk. All right, permutations and combinations. I think we did several of these in class. So I'm going to do 43 and 45 because they do a really good job of giving examples of permutations and combinations. Permutations has a formula. It's the number of objects, factorial, which means to multiply it. So like 5 factorial would be 5 times 4 times 3 times 2 times 1 over n minus r factorial, where r is the number that we're taking at a time. So like in the first example, we've got 25 people. We're going to take 8 of them at a time. This would be n and this would be r. So identifying n and r is not too difficult. Usually the biggest one is n. With the combinations, or the hard part is knowing whether it's combinations or permutations. So combination is n factorial over r factorial times n minus r factorial. And these formulas look way more complicated than they actually are. It's just a way of saying something that's not too tough. The difference between these two, permutation, order matters. First place is different than third place, okay? You get a different medal, so the order you come in matters. But if we're just talking about the top three, and it doesn't matter whether you get first or whether you get second or whether you get third, you just podium, that's all that matters. That would be a combination. Order doesn't matter. Let's see, combinations of clothing maybe would be a good example. If I'm going to pick out 3 articles of clothing, I'm going to pick shirts, then pants, then shoes. It doesn't matter if I do shirts, then shoes, then pants. It doesn't change my outfit. That would be a combination of things. Okay, so let's read the first one. Top 25 people or 25 people are going to run in a race. The top 8 advance to the finals. Okay. Do they get money for getting first instead of 7th? No. Do they get a medal? No. They just advance. So let's say we number the runners. And it just so happens that the runners 1 through 8 are the top 8 finishers. They cross the line in order. Then all 8 of them would advance. Well, what if it actually happened like this? Number 3 now has more bragging rights over number 2, but it doesn't really matter because they all advance. The order doesn't matter. Advancing to the finals is advancing to the finals. Whether you were 8th or 1st, 4th or 7th, it doesn't really matter. You're going to advance. So this is a combination. And so this would be 25 factorial over, remember we have r is 8 factorial, 25 minus 8 factorial. And so this scary formula becomes 25 factorial over 8 factorial, 17 factorial. And you may skip ahead, you may just do that in your calculator, but what happens with this is, I'm going to pause it actually. All right, I'm back and I regret nothing. Okay, so I wrote all these factorials out. This one is actually the red stuff. So what does this end up doing? Well, the 17 factorial cancels out everything below 18 from the original factorial. So these all cancel each other out. So basically, this is the number of permutations for the first 8 people coming across without order mattering. And then when we take 8 times 7 times 6 times 5, we're finding out the number of different ways those 8 people could come across. So it could be 1, 2, 3, or it could be 1, 3, 2, or it could be 3, 1, 2. There's so many different ways that could happen. And your final answer ends up being this. Now, here's the big payoff if you hung around. You can type that in your calculator, or you can say, hey, this is a combination of 25 objects. We're taking 8 of them at a time. And you can tell your calculator to do that. No exclamation points, no factorials. To write, your calculator has that programmed in. You go to math, probability, select number 3. You type in the 25, type in the 8. 1,081,575 ways that could happen. So you could be with a lot of different people at that finals race. All right, similar question. We got 35 people that are running a race. The top 3 runners earn gold, silver, and bronze medals. So we're taking how many people? Gold, silver, and bronze. That's 3 is R. There's 35 people total. That's N. And do we have a combination here or a permutation? Well, the top 3 runners are earning medals. Okay, so if they don't care what kind of medal they get, then it would be a combination, but they probably do. So this is probably going to be a permutation of 35 people taken 3 at a time. You can type that in your calculator. The formula is 35 factorial over 35 minus 3 factorial, which would give us 35 times 34 times 33. That's what that simplifies to. And why would it be that? Well, think about it. When they're running the race, you're waiting for that first person across the finish line, and they do. There's 35 possible people who could win that gold medal. But now someone has the gold slot. So how many people are left to possibly win the silver? 34. How many people are left in the bronze? 33. We can type that out. 39,270. No. You can also do probability. Same thing. 35 permutations of 3. Promise you they're the same. 39,270 different gold, silver, bronze possibilities. All right, there's part 1. Happy trails. You're doing a great job. You're almost there.